So, welcome to STAT340, the spring 2023. And my name is Lars Snepen, and this is the first lecture video. First lecture video. And it's about practicalities and exploring data. So first of all, let's just have a look at the people you will meet in this course this spring. So this is me. And my name, as I said, Lars Snepen. I'm the responsible for this course this spring. I'm a professor in bioinformatics at KBM, so I'm not really a statistician, which is perhaps a little bit strange that I'm teaching this course. Well, first of all, we are trying to sort of mix the teaching resources a little bit, and also I have to say that this is applied statistics, and bioinformatics contains quite a lot of applied statistics, so at least from the applied perspective, a bioinformatician is perhaps not so bad idea teaching this course. My office is M244 in the Dairy building if you want to try to get and visit me, have a talk or something. So all the statisticians and bioinformaticians are in this corridor, so I'm in innermost office actually. There are also some teaching assistants here, two guys, Nikolai and Øyvind. And these you will meet in the exercise classes. So these are the three of us is sort of the team that you will encounter this spring. The content of this first lecture is first a session about practicalities. We always have to start out like this, right? How do we do this course this spring? The weekly work, what is the evaluation here, the exam and so on? What kind of background should you have? And then a little bit about what we are going to talk about, even if perhaps some of it will not be very easy to grasp right now. I will just present you some headlines. And we will also briefly start working on the first sort of part of the course, namely exploring data. So we need to start a little bit carefully, of course. First week we don't, it's a sort of a half week, you could say, because the semester doesn't start until in the middle of the week. But we will have a look at these topics here. It's most about plotting and getting used to using RStudio and so on. And this is really important, right? So we will come back to this over and over and over again during the spring, but we have to start out somewhere. So the practicalities. Let's have a look at those. So here is the sort of the schedule for a week that you can find in this timeplan on the web. And the lectures are said to be Tuesdays from 2 to 4 here. But in reality, this is not going to be lecture hours, because all the lectures will be like this video here, recorded videos that I make before the week starts. So I will actually put out these videos, try to do it on Monday after lunch sometime. And in these 2 hours here on a Tuesday, in this room here, you can actually come there. I will be there. You can come there and we can have some talk about these videos, right? So instead of having a sort of a one-way communication where I am lecturing something, I am doing the one-way communication here as in the videos, and then you can come and we can have a two-way communication about the topics. But I will not present anything new or other than in the videos on these 2 hours here. So if you don't show up, you will not miss anything. If everything is very clear in the videos, it's not like you have to show up here. But in case you want to discuss something. The exercises. I will also put out the exercises on Monday afternoons. And then you can come and get help for the exercises at these hours here. First here on Thursdays, and then on the following Monday here. And there is no reservation of any time, you could say, so everyone can show up at any time. This is the best as long as it works, right? So please don't everyone show up at exactly the same time, because then it will be a queue, right? Too much for the teaching assistants. So that's where you meet the teaching assistant. I will also probably be there from time to time, at least in these exercise hours here. And again, you work with the exercises once they have been launched, work in groups or whatever. I would recommend that if you can. And then you show up here to get help of whatever you found difficult, right? So this is sort of a service. We provide this service. You don't have to show up, and you can show up whenever you like. You can come at all these hours, right? So our week actually starts on a Tuesday then. We sort of start by this Tuesday here, or actually the Monday afternoon, you could say. And it ends in the following Monday. So it looks like this, and then ends here. So this is the sort of schedule we will use for the whole spring now. And notice that later in the spring there are some Mondays that disappear due to holidays. In Easter, and also I think the 1st of May is a Monday. So some of the Mondays will be lost, but that's not catastrophic, right? Because I put out the lecture videos, and we have the Thursday hours at least. So should we meet physically or by Zoom, digitally? And this is a question that has been relevant for the last couple of years now, or actually, yeah, a couple of years ago there was no alternative but Zoom. But now we have the possibility to choose. We have these rooms reserved, and we will use them. Notice this room here in the tower building. It doesn't take too many people, so please don't. We cannot come all at the same time there, right? But we will start out using these rooms for physical meeting. That's how we will start out. But I will also hand out a questionnaire about this early now in the course, because I know that there are some of you who, for practical reasons, also would like to meet digitally, because you are not physically present at campus, at least from time to time. So it may be that we provide this as a service. We say that, okay, at some of these times we only meet digitally on Zoom. But this depends on the feedback we get, and also if people actually show up. Because last year we did this as well. We had both physical and digital meeting, but people didn't show up. So it doesn't help to say that you want it. You also have to show up and actually use it. We don't have resources to have it going if no one's using it. But we will come back to this. But we start out with physical meetings. That's how we start out. So please show up first week at least. The evaluation here, well, there are first of all 4 compulsory assignments during the spring. And this year I have changed it a little bit, so it is like this. The first 3 assignments are actually just like the weekly exercises, but you have to hand in a small report. We will come back to how to do that practically. The first one is in February, so it will be launched pretty soon. The next one is then early March and then late March, just before the Easter. And then there is one after the Easter in April, in late April, I think. And the last one is different. That's a quiz. And that is because this will, look more like the exam. The first 3 are more sort of practical data analysis, while the last one is more questionnaire like you will get in the exam. So that's why I make it a quiz in Canvas. But the point is, you have to pass 3 out of these 4. 3 out of the 4. You can do all 4, of course, but at least 3 out of the 4. If you don't do that, you will not get a grade. There is no grade on this. It's only passed or failed, but you have to pass them. Then we have the exam, and that's the date is not set. It's in May sometime, last half of May, I suppose. But the date will be set, I guess, sometime during the semester. It's not me that chooses this, right? Please be aware of that. We have nothing to do with the exam itself, the practicalities. It's a multiple choice type of exam in ViceFlow, right? So, and it's an open book exam, so you can bring stuff, but you cannot. But you have to bring it on paper because your computer will be locked during the exam. You will not be able to run RStudio or things like that in the exam. But the questions are not of that kind either. So please be aware of this. You can bring paper, right? And notes if you like, but you have to have them printed out. You cannot use your own computer for more than just doing the exam. But I hope you are used to doing this ViceFlow exams now. You have done this for quite some years. But we will come back to that. I should also point out to you that, as I said, none of us at KBM are actually involved in arranging this exam. So if you have any questions relating to the exams, if you are registered for the exam, when will the exam be, what are the sort of rules surrounding the exams and stuff, please don't ask me. This is not my sort of responsibility. I know nothing about this. I make the exam questions and hand it to the study administration, and then I never see anything more of it. So all practical questions must be related to this study administration at the NMBU. Okay, what is required of your background for taking this course? Well, first of all, you should have some background in basic statistics, like the STAT340, which is the beginner's course here at NMBU, or something similar from other university. I guess the beginner's course in statistics are pretty sort of similar across the world. So they contain some topics here. I think you can manage very well in this course, even if this was some time ago. You should just repeat a little bit what you have heard about. I will not go into the details of this in this course. So we just expect you to know these words and phrases. And I should say this is a very sort of applied course, so we will not dig into the theory very much in this course. What is perhaps more important is this: R and RStudio. Being used to using R and RStudio, that's really an advantage, because that's what practical data analysis is all about. So if this is something you don't have, you should put your emphasis on this now in the beginning. You have to get used to using RStudio and basic R skills, basic coding. We will not do much coding here, but a little bit. It's unavoidable. So week 1 exercise has been designed to sort of get you started here in case you haven't the skills needed, or if you have, you can actually just look at this exercise to sort of relax and see that, okay, this is what I need. So please do that. The topics we will visit in this course, well, it's like in the previous years. I haven't changed it very much. What I have changed is the order of the topics. So the first part I call exploring data, and that's the first 3 weeks. That's today with basics and some plotting. We will not be able to do very much the first week. Then on the second week, I will talk about PCA, or actually ordination as I call it here. principal component analysis, and also a little bit about multidimensional scaling, which is sort of related to PCA. It's just a small addition here. Then in week 3 we will talk about clustering methods. And all these are sort of exploring data. We are not doing any modeling. We are not sort of testing any hypothesis or stuff like that. It's all about trying to overview and get some ideas, you could say, about our data. Then we start data modeling. And this is sort of the main part of the course, you could say. Data modeling. Basic regression and ANOVA. That's a couple of weeks here. Variable selection I highlight as a sort of a topic of its own. I will spend a week only on this topic. And then we will also see some alternatives to variable selection, compression methods, and related to that again, a little bit on non-parametric methods. But this is not a big topic, but it sort of relates to this here. It could have been a much bigger topic, I think, non-parametric methods, but I think that will be some debate among the teachers for later, if that should be the case. Then a couple of weeks of mixed models, which is sort of just an extension to this first here. It's all about linear models. And 2 weeks for that. Then we have Easter holidays, but after the Easter we will talk a little bit about classification methods, linear discriminant analysis, and logistic regression. Those are the 2 sort of basic machineries that we will dig into here. And finally a little bit on Poisson regression at the very end. And I have to say that for this particular topic, I will have a guest, another colleague of mine, Tore Egeland, will come and talk about this. So this is not my stuff, you could say, but all the others are. So I will try to do my best. I have to confess that not all of these topics are things I do every day. So some of the topics I know better than others, but we will try to manage. I should also say that things may happen, of course, during the semester. So this schedule here is not like the final one. We will maybe have to adapt. Diseases and stuff may happen, right? So we have actually an extra week here that we can make use of if needed. Yeah, it has turned out to be useful in the past to have this sort of buffer week. And if we don't use it, we can do it for just repeating for the exam in the end here. Okay. The curriculum for this course consists of all these lectures, presentations, the videos, and the presentations, all the exercises, and also all the assignments that we give. So all of this this is sort of the most important, because this highlights what we are going to focus on, right? There is a textbook that we use sort of from briefly, I could say. We just link to it from time to time. It's a free book. It's called the R book. It's pretty thick, so it contains a lot more than what we are visiting in this course. You can download it as a PDF and start to look at it. The first 8 chapters are sort of repetition or things we are not digging into here. You can look at them if you like. So it means there is a lot here for giving you some background, much more than you actually need for this course. And these are the chapters in the book that we will probably, or that is most relevant for us, right? We will give some links to that for every lecture. Where can you find the topic in this book? There is also another book which is not sort of required, but I would actually recommend you, especially if you have a little bit mathematical background. This is really a good book, in many ways much better than this one up here, which is very practical. It's the R book, you can understand by the name. This focuses a lot on R, how do you do it in R, right? But it doesn't really explain very much how things really work. And that's the difference here. This focuses much more on the methods. It also uses R in its exercises. So if you want to learn a little bit more than what you learn in this course also, this is a good book. This is actually a sort of a smaller version of a much bigger book, which is even better, but that's really too heavy for this course. But this one is nice. It's also free. RStudio is of course super important. We can't do any practical data analysis without a software tool, and RStudio is the one we use. So you have to install R, and please note the order of things here. First you install R as a software, which is not RStudio, and then after you have installed R, you install RStudio, because RStudio is sort of a desktop solution, you could say, to running R. R itself is not very graphical and nice to use. It's sort of the computational machinery, but this is the sort of the windows that appear on your screen, right? It's called an integrated development environment, IDE. Yeah. You also need to install some R packages, and we will do that as we go along. And I should immediately say, and you will see that in the first week exercises, we have actually a data package, an R package containing datasets that you should install immediately, because all the datasets we use in this course, I think, will be from this R package here. So it's really important that you install this R package here. Otherwise you will not get the data, because we will not put the data out as files. That's a good reason for that, because reading data from files always create a lot of problems for people who are new to R and RStudio. And this is not really a course in R coding. So we will not, we wouldn't like to spend a lot of time reading data from files and all the hassle that it creates. So we like to just load the data directly from this R package. So week one is how to get started with all these practicalities here. Okay, let's start exploring some data. So first of all, the language of tidy data. So what am I talking about here? Well, we typically arrange data in tables. At least that's the word I would use, a table. Right? In R, when it comes to implementing this in R, the table is either what is called a data frame or a tibble. And it doesn't really matter much to us whether it's a data frame or a tibble. These are sort of two sort of technical ways of implementing a table in R. A table is always a series of columns, not a series of rows. The columns are the sort of entities of a table. And this you also recognize from spreadsheet, like Excel, for instance. Columns are the entities. So when you draw a table, when I draw a table, I always draw it like this, right? It's a series of columns hanging down next to each other like this, and there is no link between in this direction, right? The link is in this direction only. Each column is what we call in statistics a variable, or at least in practical data analysis like this. Think of each column as a variable and not parameter, which is I hear people talk about variables as if they were parameters. We measure the parameter, they say. You cannot measure a parameter, but we can come back to that later. So what you measure is a variable, and all the measurements you have are stored in tables, and each column of that table is what we call a variable. So here we have names, of course, on the columns. That's very typical. We always have names on them to describe what's in that column. And notice that each column in an R table is a vector. A vector. This is a vector of dates. This is a vector of prices. This is a vector of names. And I have colored them differently here to indicate that these are of different data types. We will come back to that. Each row in such a data table we call a data case, right? And these are typically what we also sometimes refer to as our samples, right? Because each time you go out and measure something on a new individual or a new location or a new time point or whatever, you measure these variables and add them as a new row to your table, right? So that's the data case. I think that's a phrase I will try to use during this course. Variables are columns, data cases are rows of this table. So by convention in statistics, we also like to use this letter N as the number of rows in such a table, and the letter P as the number of columns or variables in such a table. So you will frequently see that, N and P. I will also use this during the course. And please remember, N is the number of rows, P is the number of columns in such a data table or data set. Okay, data types, yeah. So in the table, different column may have different data types. And that's sort of characteristic of a table, that each new column may be different from the previous columns. But within a column, all the data must have the same type. And that's also the coloring here, right? So you see that down in this column, all the cells are yellow. All the cells here are blue. All the cells are green. But the color between the columns can differ, but not down within one column. In STAT340, we typically see two types of data, or data types, right? Numerical data, which is in R either of type numerical or integer, and that's numbers, right? So for instance here, this column here, prices, I guess will be numerical, right? These are numbers, quantities, right? Also I guess date, even if date is a data type in itself in R, when it comes to using it in data analysis, we typically convert it to some numerical variable. But actually in STAT340 we will not deal specifically with dates as a data type. We think of it as just integers, for instance, days number, right? 1, 2, 3, 10, whatever, or time points of other sizes. The other types of data we will see a lot in this course is categorical data. And in R, that's typically what we call a factor. It is, however, sometimes just given as text. Character is another word for text in R. And this column over here, the name, will typically be of this type, right? A name is a text. And this is not numerical, right? There is no numbers here, it's only text. But we will see factors, which is then typically text of where you have the same text appearing over and over several times. So it's like categories, right? Each new text is a new category. We will come back to that. Numerical data or categorical data. That's the two data types we will see. There are also, of course, logic data type in R. We may see it from time to time, but rarely as data. A logic can only have two values, true or false. And we never really have data of that type. If we have sort of binary data, you could say, I mean data which is categorical with two categories, we store it as a factor, actually, with two levels, right? Not as a logic. That's a logic is purely for sort of what should I say, programmatic use, not as a data type. We may sometimes transpose a data table, and what do we mean by that? It means that we just sort of grab the table at this corner and flip it around, so that what used to be the first column becomes the first row, and what used to be the last column becomes the last row. So you just what used to be columns become rows instead, and that is not really in general possible in R, but it is possible if all the data of all the columns are the same type. Only possible if all the variables are the same type. So if all the columns are numerical, for instance, numbers all over the place, then you can transpose. Because then in the transposed version, still all the data in the same column is of the same type. And of course, it's not surprising that if you have a data table where you mix numbers and text, we will from time to time only look at the numerical variables, sort of peel away the text and do, because that's where you can do computations, right, on numerical variables. But in general, tables contain both numbers and text, you could say, or factors actually. I should say a few words about data wrangling, because what does it mean? Well, it's all the processing of the data needed in addition to the data analysis, you could say. Or you could put it like this: data wrangling is what you do if what you get in is data and what you get out is also data. Then you do data wrangling, right? And so it means all kinds of sort of shuffling, reordering and stuff that you do with your data is data wrangling. Data analysis, that's also data in, but it's not data out, it's information out. You make some conclusions, right? You get some information from your data. Then you do data analysis. This course will be on the latter here, data analysis. But in reality, data wrangling takes the majority of the time in all practical data analysis. So this part here is actually, in that term, more important than this part here. So wrangling requires coding, and that's where the really sort of big coding part of a practical data analysis comes in. It's the wrangling part. In STAT340, we try to focus on data analysis, not on the data wrangling, because we have another course for that, STAT300. That's data wrangling. However, some coding is unavailable, so some data wrangling we will also see here, because it's not possible to avoid it. And in week 1 we have some exercises and links to STAT300 and some other resources in order to sort of repeat or practice on this data wrangling part. But again, we try to focus on the analysis part here. So if you want, if you feel that the data wrangling is what you lack, you should take this course here, STAT300. It's in the January block. Okay, summary statistics. So let's start exploring data. Once we have loaded the data set, we should always explore the data. And the first thing we would like to do is ask this type of questions. What data types are the variable? That's of course pretty obvious, right? What's in the columns? Is it numbers or text or factors or whatever, right? Are there any missing data? And that's also important, we will see shortly, to verify if there are some holes, you could say, in the data set. Because that's pretty often happens in practical real life. For some reason, some measurements haven't been made. Are there any severe outliers? And what do I mean by that? And that is typically data where we have perhaps mistyped something so that the numbers come out completely wrong, right? And this is also something that happens from time to time, right? What is the distribution of categories if you have categorical data? So that's sort of because outliers is only something you can do for numerical data, right? If numbers are, let's say you are measuring weights of people, right, in kilograms, and then suddenly there's a number saying 100,000. Then you realize this is not really, this must be something wrong, right? Because no one can weigh 100,000 kilos. And these type of severe outliers happen. So it's important to sort of be aware of them right away and fix this, right? The same with the categories. If you have categories, for instance, male and female, and then suddenly there's a third category, then there must be possibly something wrong here, right? You have typed male or female in the wrong way, so it turns out as a different text, right? So that's why it's important to do this exploration here immediately once you read in the data. So let's see how we can do this in R and at the same time start using RStudio. You will see I have these R sessions from time to time during these lecture videos. Okay, so here I have started RStudio now, and the very first thing I would like you to do is to create a folder where you can have your STAT340 stuff. So I created this on the C column here, so if you use this, if you open this files pane, wherever it is in your RStudio, you can maneuver here like you do in file system in general, right? So I created now a folder on the C column, which is sort of the top of the file tree, at least on the Windows computer. But you can create it anywhere, right? In your documents or whatever. It doesn't matter. I made it here. And then I jump into that folder, and then it's important to remember to set your working directory, right? Because when you're working in R, it's always a folder where you sort of run your code, and I would like that to be this folder now. Set as working directory. And then you can see up here above in the console window, at the top of the console window, you have listed the same path down to this folder as I have here. Yeah. Otherwise, you will not. If you try to run code in a different folder, it may not work, right? For obvious reasons, the code is not there. So let's start making a new script here now. New file, new R script. I make a straightforward R script. So this is now an empty file, you could say, without a name. And here I can now start filling in code. Let's just save it immediately. Save, and I think I would, and please notice now that you actually save it in that folder and give it a proper name. I think I will call it week 1. Or actually, I have this habit of calling all my R script starting with script underscore and then some text that describe what this is about. Week 1. And then it should appear here with the extension .r, as all R scripts should have. Now, before we do anything else, let me visit this lecture document here. And this is what you find on Canvas, right? So the point is now that the code that I'm going through here in this videos is exactly the same code you find in these documents. So you should do this yourself. You should do exactly what I'm doing here in the video now yourself, if this is something which is new to you. So, and if it's not, you can just look at the video and see, okay, I know how to do this, so you don't have to do it. But here I do it. So what I do now, I just copy this code here, from this first session, loading a data set, right? And then I paste it into here to my script. So here we now load this bias data R package. And of course, in order to be able to do that, I have to have installed this package first. And if you look up your packages tab somewhere on RStudio, it should list all the R packages you have installed, and in that list you should find that package. And if it doesn't appear, sorry, here it is, bias data. If it doesn't appear, you have to install it. So see the first week exercises on how to do that. I will not go through that here. So now let's save the file again. So now you can see it's saved, it's no longer red. And then we can run this code, and we can do it step by step by just putting the cursor like this and run one line at a time. And notice now it was this checkbox here is checked, indicating now this package is loaded, ready to use. And now we can start loading the first data set. Audi. Yeah. And down here in the environment window, I can now see that this data set is actually available. It's not really loaded yet. It says promise here. Yeah. Once we start doing something to it, it will be sort of loaded. Notice you can also change the appearance here between list or grid, and some the output will change. So I like the grid output. You can choose. Okay, that's the first thing, loading the dataset. Let's go back to this lecture document. We should look at some summary statistics, wasn't it? How do we sort of explore this data? To see what's in the dataset, and then we use the summary function, for instance, and that's really convenient. The summary of a table will give you some summary output, and now I should make the console window here a little bit bigger so that we can actually see what it outputs. So if I run this code now, we will see that this gives now a summary of each column in this dataset. So we can see there is a column called price with some numbers, numerical, right? km, kilometers, I think. These are car data. Audi is a car. So it's the price of the cars, how long they have run, and so on, the horsepowers. And this is the transition. And this is a different data type, right? So this is not numbers. It's either A or M. And this is exactly what we call a categorical variable, a factor. And we can see there are 8 A's and 22 M's here. We can also inspect the table once we have it in our environment window like this. It appears this small table-like picture here. If you click on it, you can open it here in our studio viewer here to look at the table. You cannot do anything to the data in this viewer here. You can only look at them. Well, you can sort the columns, but it will not actually do anything to the original table. And that's good, because we don't want clicking here to change our data. So here we can now see that this is numbers, yes, numbers, and here you have this factor with either M or A as sort of texts, right? And here's another factor, also consisting of 2 different types. I think if we go back to the summary here, we can see that. Yeah, here, fuel, either D for diesel or G for gasoline, I think. But all the other ones are numerical. So the summary will give us an idea about the data types. It will also give us some idea about the values. If we click out this one again and go back to the summary. So here you can see the minimum and the maximum value. And that's something you should have a look at, right? To see if these, because these are the most extreme values. Are these reasonable values, or are there some really mistypes in here that make some of the values way out of proportions, right? So have a look at these extremes to verify this. Is this reasonable value? And then of course median and mean values, and that's not so important because they will always be sort of reasonable values, I suppose. Okay, if we go back to the summary document, the lecture document here, missing data. Yeah, how about missing data? We can actually look into the data and see if there are some missing data, for instance, by using this code here. And what is this? Well, this function here, taking Audi table as input, will now detect if there are some missing data. And why is it called isNA? Because a missing data point in R is always coded as NA, not available. So this function here will simply go through all the cells you can think of in the data table, all the cells, and look if there is NA for missing somewhere. And then we do a column sum of that again. So we sum up for each column how many missing data are there in each column. So if I run this particular code here, we will get an output here in the console saying that in the first column price there are 0 missing. In the second column KM there is 0 missing again. And we can see there are actually no missing data in any of these columns, and that's good, right? But this is something we can which is convenient to overlook, right? Especially if you have data set from files, right? We read them from files. I guess that in the data sets we are looking at in this course, there will not be many holes or NAs because we have sort of fixed them already. But in your own data sets, this may happen. Let me briefly go back to the lecture document again, because we should explore a little bit more this NA. Why is this important to know? Let me create a simple vector here now containing these values, and notice I now put NA in the middle here as the fourth element. And notice that RStudio will color this text differently because it recognizes it. NA with capital letters is a special symbol in R. So if I create this vector here called X, it will appear here. Think of it as a column that has been sort of taken out of some table. So now it appears here on its own, sort of. If I just type X, and it will be displayed as a row here, but it's actually, think of it as a column in a table. And then we can see the element number 4 is now NA. So if we now take the mean value, the average of this here, what happens? Well, let me compute the mean of this X, and then you can see it becomes also NA. And this is quite typical. Many R functions behave like this. If you feed them some data, you feed X as input to this function, and if that data contains some NA, and it can only be one single one, then the whole result will be NA. It's not possible to compute the mean value when you don't have all the values, right? So, and this may happen, right? If you have a big table and far way down in one column there is an NA, and then you start to do something to this data, and suddenly all the results come out like this. That's catastrophic, right? So you need to be aware of these holes in your data. So that's why we always go looking for this. So you can actually repair this behavior of the average of this mean function like this. You can say that, okay, remove the NAs before you do the mean computation. That's what this option here is doing. So we use the same function, but we, in addition to just giving the input, we say NA remove equals true, means remove the NAs before you do the computations, and then you compute the mean value from the rest of the numerical values, right? And then you just sort of forget this one as if it was not there at all. But the default behavior is to do not forget it in R. And I think that's a good design. We should not compute mean values when we have missing values unless we know exactly what we are doing. So that's important, knowing where you have the NAs. So I actually made a small function in our data package for overviewing big data sets. Let's see what I mean. Here I load another data set from my data package called column. Right? So let's load this data set first, like this. And here you can see the column appeared now. And if we now try to run the summary like we did before, summary of column, yeah, this will work, but the output is horrible. The output is horrible because this data set contains a lot of columns, right? So you can see it contains 1989 columns. And this summary will try to output something for each column, and that's it fills up the whole output buffer without actually outputting anything but the column names. So this summary function doesn't work very well on big data sets, so that's why I made a summary function instead, which is sort of summary for big data, you could say. But you can use it instead of the summary function on any data actually. So if I just copy this, oops, I shouldn't have cut it, I should have copied it. If I run it here, directly like this, it will output the summary, more or less the same summary, but in a different format. So now we will have each of the original columns is now a row in this table. So here the first column is now the name of the variable. The first variable is named tissue. The type of it is factor. How many cases are there? How many rows, right? 62. How many of these are missing? 0. So this is also sort of a nice addition to this summary function, that it also immediately lists how many missing data. Notice the summary didn't do that. The minimum value here, well, there is no minimum on a factor, right? So when the data set, when the variable is a factor, these are NA, because there is no minimum, quantile, median, and so on. So these are just empty. But if the next variable, which is numeric, we can see that we have some values here. Minimum, quantile, median, and so on. And also the mean value and stuff. Yeah, it continues down here. Maximum value is here. So it outputs the same as the summary plus a little bit more. Yeah, and if you have categories, it will list how many you have in each category here. Number of categories, 2, 40 in one of the categories, 22 in the second one. And of course, since this function outputs a table, we should store it as a table. So that's what I do here. If I run this code again, it will not output to the screen here, but it will store the output in this table. And now we can actually view the table here instead by clicking it open. I think this is a much better view of the summary, right? So now we can see the first variable is called tissue. It's a factor. It has 62 rows, no missing data, and it has 2 category levels, where we have the first level is called tumor, 40 cases. The second one is called normal, and it's 22 cases. And all the numerical variables have the summary values here, and no categories, of course. So this is an alternative way of just summarizing your data. But you need the data, you need this bias. It's not part of R from the beginning like summary is. It's a special function in that bias data package. But once you have loaded this one, you can start using this.
as an alternative summary. I think it's slightly better than the original. So once we have started to explore our data, we quickly want to do some basic plotting, and we will do a lot of plotting this spring of data. So let's see some basic plots here. Well, first of all, I like to point out how important plotting is to data analysis. We can compute all kinds of stuff and p-values and estimates of this and that, but when at the end of the day, if you want to sort of tell someone about your results, plotting is really, really important. So never sort of estimate how important it is to make good plots. We will look at some very basic types of plots that we very often use, but these are not the only ones we use, but these are the most frequently used. The scatter plots, the bar charts, histograms, and box plots. And these are the ones we will see most frequently in this course. And I think we have to go back to our studio and look at this in real life in order to get some real understanding of it. Okay, let's go back and see what the lecture document says about basic plotting. Here it is, the scatter plots. So that's what we typically use to display two numerical variables and how they are related. And I should say immediately now that the plotting I'm doing here, in R you can do plotting in many different ways. I will focus on the ggplot way of doing it. And the reason for this is that this is the sort of most used way of plotting in R. I think that actually the main reason for many people to use R is to get access to this ggplot. So let me copy this code. So you should invest some time into getting used to doing it this way. It's not the easiest way to plot. There are some other ways of plotting in R which is easier, but they don't have the same potential, right? It's a shorter starting threshold, a smaller threshold for starting, but it doesn't have the same potential. You can do a lot in ggplot. So in order to use ggplot, we need the tidyverse packages. You should install the tidyverse packages, and that's also part of week 1 exercises. And this is a collection of many packages that we will use all the time. All the time. So please install the tidyverse packages along with the bias data. That's the first thing you will ever do. And here is some code for making a plot using the Audi data that we loaded above here. And you can see the code like this, ggplot, with the input, the table that you want to take the data from. That's typical, right? And then this plus, and this is characteristic to ggplot. This only works in this way in ggplot. Otherwise, plus is the ordinary plus operator, but here it has a different meaning. It means you add something to the plot. And what do we add? We add geoms, as we call them, and think of them as sort of layers that you add to the plot. So we want to add a geom called geom point, and that's the one we use to get scatter plots. And then we have to select what's on the x-axis and what's on the y-axis, and this should then typically be numerical variables, right? From that we can open the Audi table here again. Price is numerical, and what was the other one? Age. Sorry, Audi table. Price is numerical and age is numerical over here, first and last columns. And then we can add some text on the axis, we will see, and then we actually print the plot, because here I store the plot into this object here, and then I print the object to get it actually visible. Because if I run this code, first let me run this tidyverse, and that will attach some packages and blah 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 like this. But once this is loaded, we can start plotting, and then I run this code, and this is now running these three lines, right? This is actually one line of code. That's why this plus operator is used here. You can start a new line, and after the plus you typically start a new. You don't have to start a new line, but that's what we typically do to make it easy to grasp. We first create the plot, right? Then we add some geom, which will be the sort of the how the plot looks like, you could say, and then we add some text to the plot. You can continue adding more and more and more stuff. And then we finally print the object. So now the object is just created, but it's not, we don't see the plot anywhere, right? But we can see the object is actually created here. In the environment window, we see it. It's a GG object. And now we print it. And then in the plotting window, you should see something, right? So here we now see a scatter plot, where each dot corresponds to a data case. Each dot is now corresponding to a row in the table. If you let's take this dot here, for instance, it has an age of this value. You have the age axis down here, right? And you have a price on this of this value. So I don't know which row it is. This one could be any of the rows, right? You have to look up the rows where the age is like this, the smallest age. Actually, if we just click on this and sort by age, I think this must be the row number 29, because it has age 3, and that is down here, right? And it has price 330, which is in here, right? So each dot is now a row in the table, corresponds to a car or a sample or a data case, right? And we can clearly see that as age is getting larger, the price is getting lower, right? And that is also what we expect with automobiles, right? With cars. The older it is, the cheaper it is. So that's the basic scatter plot. Let's go back and see some. Yeah, here is another version of actually the same plot. Instead of using points, we use a line. Let me just do that. It's not a very, because sometimes we will see later that we replace geom point with geom line. And what does it mean? It means that it draws, instead of making the plot as separate dots like this, it draws a line between them. So let me illustrate. It's not very successful here because the points are not ordered along that axis here, right? So these lines goes in all kinds of directions here. This is really horrible, right? This was not a very pretty figure. The previous one was much prettier, right? But it's nice to know that you can make a scatter plot also with lines, right? You just replace geom point with geom line. Otherwise, it's similar. Yeah. If we had ordered the values on the x-axis, the lines would look prettier, I think. Let's go back and see bar charts, because that's also important. And what is the difference between a bar chart and a scatter plot? Well, it's actually not that big difference. But here because again we have an x and a y axis like we had in the scatter plot, but now we typically plot on the y axis the counts of something. And also on the x axis, things should be ordered, right? So we typically use a bar chart when we have either a factor variable, a categorical variable. We count how many occurrences we have of each factor category or level. Or like in this case, we have a variable called year, which is actually numerical, but it's nice in the sense that it contains evenly sort of spaced values. It's 2011, 2012, 2013, 2014. You can see that all these values are sort of with the same distance between them, right? And then a bar chart can look good. Let me make a bar chart like this. And notice we use the geom bar in this case. So we only use an X variable here because the geom bar will then count the number of occurrences of each value of year. Let me plot and you will understand what I mean. So 2005 occurs this many times, right? 8. 2006 occurs this many times, 1, I suppose. 2007 occurs 3 times, and so on. So this is a bar chart now. I notice we only fed it as input the year variable here, and this geom bar will by itself start counting the number of occurrences of each distinct value here, and plot them in this order because they are numerical variables. And that's also why you see it says 2005.0 and it says 2007.5. That's really strange because there is no 2007.5, because it looks at this as values, right? Numerical values. So in some cases when we do bar charts, we have actually done this counting ourselves before we do the plotting, and that's quite common, I think. So let me present you some small code here for doing that. So instead of just sending the variable to this geom bar and let the geom bar do the counting, we typically do the counting ourselves before we plot. So here is how I do this counting. I use a function in R called table, and that will actually do this counting. So if I run only this count code here and look at that tabulated object now, it will contain these counts, right? For 2005 there were 9 occurrences, 2006 1 occurrence, and so on. And now I put this into a new table. I create myself a new table here now, where I say that n cars, that's the counts. That's simply converting this tabulator into integer vector, because it's not really an integer vector. And then I say create another column called year, which is actually the names of this int, and that's the values you see up here, right? These are the names above each count. And you can't see it here in the console window, but the values here are numerical, while the names are texts. So this column here will now be text. So if I run this code as well, Audi counts, we can have a look at that table, and you will see it here. The counts in one column and the year in the next column. And if I run this summary function on this table now, Audi counts, we will see that this one is an integer, yes, while the other one is a character. It's text. So now we can plot again. Oops, sorry. In a slightly different way and make a bar chart again. So let me put the code here. First of all, notice I don't store this in an object like I did up here, and that's just to illustrate that you can actually do it like this. You don't have to store the ggplot result in an object like we did up here. You can just do it like this, and then it will be printed immediately. But then you cannot go back and change it like we can here. You have to run the code each time you plot. But that's we do both. Sometimes we do it like this, sometimes we do it like this. We will see both. Notice instead of geom bar, I now use what is called geom col, which is almost the same thing. But notice that geom col takes both values on the x-axis and on the y-axis, just like we did for the scatter plot. So now we put on the x-axis the same as we did up here, but we now have already the counts. that we want to have on the y-axis. So if I plot this, it should be a similar picture, right? Because the counts are the same. But notice now how the x-axis is labeled with every single year as a text. These are no longer values, right? In the previous plot, these are values. So the 2005, 2006, 2007, it's simply the values. But now there are no longer values; they are simply texts. So they could have come in any order, you could say. We could have had 2005 in the middle of here, 2007 at the first one, because they have no ordering anymore, right? And the reason they come out in the sort of correct order, you can say, is simply because it's sorted alphabetically. And since a text containing numbers, the alphabetical order of a text containing numbers will be the numerical order. But this is something you will notice from time to time, but so that it will come out in the wrong order if your labels are texts. But we will look at that later. But at least you can see a bar chart again. Actually the same information, right, as in the previous one. But we used a slightly different way to get there. And I think actually the latter one here is most common. At least I use it more frequently than this one. That was bar charts. Histograms. What about histogram? Well, that's typically something we do in statistics to look at the distributions, right? So a histogram is different from a bar chart in the sense that it's not a display of two variables against each other. A bar chart is always a display of two variables. One variable along the x-axis and some counts along the y-axis, right? A histogram only has an x-axis. And it will now chop this variable into bins or intervals and then count how many occurrences we have in each interval. So if we take a numerical variable like this, we typically have only numerical variables as input to histograms. It looks like this. And now we use the bin width of 50. So each column here now, or bar, has a width of 50. 50, 50, 50, and so on. And then we have the counts. How many occurrences did we have inside this interval? Inside this there were 0 counts. Inside here there were 8 counts, something like that. So this gives us a distribution, right? And if you change the size of this bin, it will of course look slightly different because then the intervals get bigger, right? So now they are 100 wide. And that gives us a distribution, right, of the variable. How often do we see values of this quantity and this and this and so on. So histograms we use quite a lot. The box plot is also sort of a histogram, or not a histogram, but it also compares, it also shows distribution, but it compares between different variables or different categories. So here we have then the variable to put on the x-axis, and this is the y-axis. And notice now the variable we put on the x-axis is a categorical one. If we go to the Audi table, the fuel, right? It's either G or D. So what we do now is we make a box plot, as we say, and we split the data by which category fuel they have. So the data cases, the rows where we have diesel fuel and those with gasoline fuel, are split into two groups now. And then we display how the weights are for the two categories. Let me show the plot and we will understand. So on the x-axis we have the two categories, diesel or gasoline, right? And on the y-axis we have weights. And these are now the weights for the diesel cars, right? And the thick bar here is the median value. The box surrounding it is the 25% and 27% quantiles. So it means that the middle 50% of the values are of the weights are inside here, 25 most extreme out there and 25% most extreme out there. And the same here. So now you can compare weights between diesel cars and gasoline cars, right? We can see that diesel cars are heavier because this thick line is above this thick line, the median. And we can also see the spread, right? This is how much it varies within diesel cars, and this is how much it varies within gasoline cars. So this is an alternative of looking at the distribution of the data, right? Either between different variables or between different categories of data. Typically the latter. So, and it's also a distribution, right? It says something about the most extreme values in same as we did for the histogram. Actually, you can see the most extreme in either end here, right? But in the histogram, the weights are on the x-axis, while in a box plot, the weight will now be, or the measured variable will be on the y-axis instead. Finally, a few words about centering and standardization of data. So what do we mean by this? So many times we want to center or standardize numerical variables. And what does it mean? And notice we can only do this for numerical variables. It's only meaningful. And why we do it, we will actually come back more to next week when we start doing principal component analysis. But you should notice right away that any correlations between the variables that we saw in the scatter plot will not change by doing this centering and standardization. So what does it mean to center a variable, a column, right? Well, you compute its mean value, and then you subtract this from all the values in the column. Compute the mean value of the column, and then subtract it from all the values in the column. So it means that after you have done the centering, the mean value in the column will become 0. Some values are positive and some are negative. Everything is sort of centered around 0. That's centering a variable. Standardizing a variable is slightly different, but also quite similar in a sense. Compute the standard deviation of the column instead, and then divide all values by this standard deviation. Right? So instead of subtracting, we divide the standard deviation, divide all values by this standard deviation. And this results in the standard deviation being 1 after you have done this of that column. So the centering means the mean value becomes 0. The standardization means the standard deviation becomes 1. We will see how we can do this shortly in RStudio. But before I do that, I want to say a few words about matrices, because we will see some example of that now. So when we do some computations later in this course, we typically want to have the data that we use for computation as vectors. And remember, all the columns in a table are vectors. The row of a table is not a vector. The row of a table is not a vector, only the columns. However, sometimes we may copy the numerical variable into a matrix. And what is a matrix? It may look like a table, but it's not really a table. And here is my picture of how I would draw a table and a matrix. And notice the difference. In a table, all the columns are the columns are the entity, and the different columns can have different data types. In a matrix, columns is not special. Rows and columns are on equal terms here. And notice all the cells must be of the same data type. Not a single deviation. So it's actually like a vector, but we just have stored the very long vector. Instead of having one super long vector down here, we have cut it up and stored it in this way instead. But think of it as a two-dimensional vector, you could say, right? But since it also has rows and columns, just like a table, people often confuse a matrix with a table and vice versa. But they are quite different. Very different, actually. And because a table can have different data types, right? And a matrix cannot. Some functions in R can work on that works on table can also take a matrix as input, because it will then convert it to a table. Notice that it's always possible to go from a matrix to a table, because you can just simply make this into separate columns, right? But the other way around is not always possible. You cannot convert a table to a matrix. So a function that requires a matrix as input may not be able to take a table as input, only if the table is containing only one data type, right? So that's why we need to be aware of the matrix, even if we like to work with tables. Some functions will require us to use matrices, and some functions, like we will see now, will output a matrix. So we need to be able to convert it to a table then. So as I said, a matrix is simply, think of it as a vector arranged in rows and columns. That's how simple it is. Also, with respect to row names, a table always have column names, I would say. It's not like it's required, but it's senseless to not have it. So we always typically have names of our columns, but we never have names on the rows in a table, I would say. It's allowed, at least for data frames, but it's sort of silly, because the text that we put as row names, we could have made them as a column inside the table. There is no reason why we couldn't do that. So we should typically have the text inside the table instead of as sort of names outside here. But on a matrix, that's different, right? Because if you have a matrix filled with numbers, you cannot have text inside it. And then it's sensible to put it as row names in addition to the column names. You typically also have column names on the matrix, but matrices also typically have row names. We will see that. Okay, so let's go back to R and finally see how we do some centering and standardization, and there we will meet the matrix. So let's see how we can do centering and standardization. First of all, let me select from this Audi table all the numerical variables. And this is how we typically select columns from a table. Not rows. Select can only select columns. And we select from this Audi table. And which columns do we select? Well, we select where the column is numeric. And this is how you can do that. You can also just name the columns, right? If we look at the Audi data, there it is. If we look at the data table here, we can just name the columns by separated by comma. But since there are so many of them, I prefer to do it like this, and I get only the numeric ones. So I run this one and get this Audi num, which is then only the numerical columns. Two of the original columns were left out here now. Okay. Let's do the centering. And this is how we do centering using the function called scale in R. And that's something which is always available. The scale function. Here I use this pipe notation, which is part of the tidyverse as well. And you will see me use this quite frequently. And if you're not used to it, you have to get used to it now, because I like to do this. When you do a series of operations on an object in R, you can do it in this way. And I think this reads much better than the alternative. So what do I want to do? I want to take this table I want to send it as input into this function here, this machine here. And the output from that I send as input to the next machine here, and so on. And when everything is done, it is stored in this object here. So this is why I like it. I like it as a sort of a pipeline, as we say. A series of operations. However, let me now just copy this function here to my console window so that we can actually, let me clean the console here a little bit. It was like that. So what you typically will see when you see the explanation for how this function works, it will then list the table, as the first input argument. The table that you want to do something with, or scale, right, in this case. And then you set center equals true to do the centering, and this other one, scale, is now turned off by setting it to false. This is the standardization. We will come back to that shortly, but for now we turn it off. So this will now take the input and do the centering only. So this line of code here is exactly the same as you get by running these two lines, right? And the reason I want to do this separately now is because I want to store the object that we get from this one into something here. I just call it M. Let me run this now here, and let's look at this M. Here it is, and notice it's a matrix. This capital M is a matrix. So if you click it open, it looks like a table here, but it's not. It's a matrix and it contains only numbers, right? And here you can now see the variables or the numbers have changed quite a lot compared to the original one, because everything is now centered around 0. So by running this code, I also take this matrix because I don't want to have it as a matrix. And that's why I do the last part of the pipeline here. I pipe that matrix into as data frame to convert it back to a table. Because remember, you can always convert a matrix to a table, but not vice versa. So let's run this one. And then we see how the centered is now the centered variables as a table here. Same values as we had in the M, and in this viewer it looks like this. It looks similar because it displays matrices and tables in the same way. But this is what we really like to have. So what happened now when we did the centering? And let's illustrate that by doing some plotting. So let me copy this code here and paste in here. So first, let's plot the original data again, and the same scatter plot as we did before, but plotting age versus price. It looks like this, right? So we have the age along this axis and the prices along this axis, and here are the cars. Each dot corresponds to a data case, a car, right? If we do exactly the same, but for the centered data, so notice the only thing I changed really is the input. Which table do we take the data from? It's now from the centered data. So if we make the plot now, of course the variables change their value because now we have 0 here as the average value along the y-axis, and we have 0 as the average value along the x-axis. But apart from that, if we compare to the previous plot, if we jump between these two plots, you can see that only thing that changes is what's on the axis, but the points are located relative to each other just as they were before. There is no change at all. We have only moved the origin into the center of the plot here. Here we have 0 versus 0. And this is important. The relations between the variables, or at least the correlations, are unchanged by this. Let's go back to the lecture document and do the standardization as well. So what is the difference? Very little, because we use exactly the same function, and the only thing we do now is we turn this one to true as well. So we turn on the centering and we also turn on the standardization. It's called scale instead of standardize, but it's the same thing here. So now if I run this one and I store this in a slightly different object, right? Instead of Audi centered, I now call it Audi centered and standardized. So let me run this code like this, and then we can do exactly the same plotting again, right? But now with this both centered and standardized. Table as data. Oops. And we get the third plot of this. And now you can see that the axis changed again compared to the previous axis and the previous axis, but the points are at the same place relative to each other, so as they were originally. The absolute distance between them has changed, but the correlations haven't. The correlation is the same. And this is something worth remembering, because we will next week we will talk about principal component analysis, and then we do always the centering and sometimes also the standardization.